Every world you see was built by violence. Mercury's iron heart, ripped from its body by a cosmic bullet. Earth's moon, torn from our planet in an explosion so massive it vaporized rock into gas. Uranus, knocked sideways like a bowling pin, now spinning on its side forever. The solar system isn't a peaceful place that evolved. It's a battlefield that survived. This is the war that built our neighborhood. Look at the planets. Really look at them. Mercury, a dense iron ball barely bigger than our moon. Venus, Earth's twin in size, but hell itself in atmosphere. Mars, half Earth's diameter with a split personality written on its surface. The gas giants. Jupiter could swallow all the other planets combined. And then there's Mars's strangest feature. One scientist couldn't explain for decades. The northern hemisphere? Smooth, flat. Featureless lowlands, like someone sanded it down. The southern hemisphere? Mountains, craters, chaos. Ancient highlands stuffed with terrain. A line cuts across the planet, the planetary equivalent of two faces stitched together. For 50 years, planetary scientists asked, why? Why does one planet look like two completely different worlds? Why does Mercury have proportionally the biggest core in the solar system? Why does Uranus orbit on its side, while every other planet spins relatively upright? The answer to all these questions is the same, and it's written in violence. In 2008, researchers at the University of Colorado ran computer simulations. They weren't looking for the answer to Mars's two faces. They were just simulating the early solar system, the chaos of planet formation. And then they saw it, an object. Between 1,600 and 2,700 kilometers in diameter. Bigger than Pluto, smaller than Mars itself. It came in at an angle. The collision released energy equivalent to 1 billion nuclear weapons detonating simultaneously. The northern hemisphere vaporized, melted, blasted into space. What remained collapsed into smooth lowlands. The southern hemisphere, shielded by the planet's bulk, survived relatively intact. One impact, one catastrophic moment 4 billion years ago. And Mars would never be the same. But here's what changed everything about how we understand the solar system. Mars wasn't special. Every world was hit like this. The debate over the late heavy bombardment, the period when these massive impacts occurred, continues today. Some scientists argue it happened around 3.9 billion years ago, a sudden, cataclysmic spike in asteroid bombardment lasting 20 to 200 million years. Others analyzing meteorite ages found evidence that the most intense bombardment ended much earlier, around 4.48 billion years ago, just 80 million years ago after the solar system formed. The Apollo astronauts brought back moon rocks. When scientists dated them, many showed similar ages, roughly 4 billion years old. Impact melt. Rock that was instantaneously liquefied by asteroid strikes. But here's the twist. Recent research suggests this clustering might be a statistical illusion. Not a sudden spike, but a continuously declining rain of impacts that we're only now learning to read correctly. What's clear is this. Between 4.5 and 3.8 billion years ago, the inner solar system was a shooting gallery. And the cause? The giant planets, Jupiter, Saturn, Uranus, Neptune, underwent rapid migration. They didn't form where they are now. Jupiter and Saturn moved inward, then tacked back outward like a sailboat. Their gravitational bullying scattered debris everywhere. Asteroids, planetesimals, failed planets, sending them screaming into the inner solar system. Earth, Mars, Venus, Mercury. All of them, scarred by violence. But 3 worlds took hits so catastrophic, they rewrote their destinies. And we're about to see how. Before 1975, scientists had 3 theories for where the moon came from. Theory 1, co-formation. Earth and moon formed together from the same cloud of debris, twins from birth. Problem? The moon's composition is too similar to Earth's mantle, not Earth's core. If they formed together, the moon should have more iron. Theory 2, capture. The moon formed elsewhere and Earth's gravity snagged it. Problem? The orbital dynamics don't work. Capturing a moon this size in a nearly circular orbit is astronomically improbable. You'd need to slow it down perfectly. There's no mechanism. Theory 3, fission. Early Earth spun so fast it flung off a chunk that became the moon. Problem? Earth would need to spin once every 2.5 hours. Nothing could make it spin that fast. All 3 theories? Dead ends. Then in 1975, at a conference in Hawaii, 2 scientists, William Hartmann and Donald Davis, proposed something radical. What if the moon wasn't born from Earth or captured by Earth? What if it was ripped from Earth? Meet Theia, named after the Greek Titan who gave birth to the moon goddess, a Mars-sized protoplanet, about 10% of Earth's mass, formed in the same orbit as proto-Earth, 60 degrees ahead or behind, trapped in what's called a Lagrange point, a gravitational sweet spot. For millions of years, Theia stayed there, stable, safe. But as it grew, gravitational perturbations from Venus nudged it loose. And 4.5 billion years ago, it fell toward Earth. Not a head-on collision. New research from 2022 shows it was likely a direct impact after all, not the glancing blow scientists once thought. Theia hit Earth at 40,000 kilometers per hour. The impact vaporized Theia's mantle, vaporized much of Earth's mantle. Rock turned to gas, iron cores merged. What remained, a ring of vaporized rock and debris orbiting Earth, a disk of molten destruction. And within hours, not millions of years, that disk began to collapse. Gravity pulled it together. The moon formed in a single day. How do we know this happened? The Apollo samples. Moon rocks brought back between 1969 and 1972. Scientists measured oxygen isotopes, specifically oxygen-17. Earth and moon rocks are nearly identical. That's strange. Different solar system bodies have different isotopic fingerprints, like cosmic DNA. If the moon formed somewhere else and was captured, it would have a different signature. It doesn't. But if most of the moon came from Earth's mantle, blasted into orbit during the impact, the similarity makes perfect sense. 2023 research shows that the moon's chlorine isotopes are slightly heavier than Earth's. Why? Because during the impact, Earth's gravity preferentially pulled lighter chlorine toward itself, leaving heavier chlorine in the forming moon. And here's the wildest part. 2023 research suggests that remnants of Theia still exist, not in space, but inside Earth. Two continent-sized blobs of dense material sit at the base of Earth's mantle, near the core. They're 2 to 3.5% denser than surrounding rock. Seismologists call them large, low-velocity provinces, LLVPs. Computer simulations show that Theia's mantle material, being denser than proto-Earth's, would have sunk and accumulated exactly where these blobs sit. Theia didn't just give us the moon. Part of it is still inside us. Mercury shouldn't be this dense. It's the smallest planet, barely bigger than our moon. But weigh it, and Mercury is the second densest object in the solar system, topped only by Earth. Why? Mercury's core takes up 70 to 85% of the planet's radius. Earth's core? Only 55%. The ratio is absurd. Mercury is essentially a naked iron ball wearing a thin, rocky jacket. For decades, scientists proposed that a giant impact stripped away Mercury's mantle, leaving the iron core exposed. Then in 2011, NASA's Messenger spacecraft arrived at Mercury and found something that broke the theory. High levels of sodium, potassium, sulfur, volatile elements. These should have been vaporized and lost in a high-temperature giant impact. But they're still there. So what happened? New research from 2025 proposes a different kind of violence. Not a head-on collision, a hit and run. Imagine proto-Mercury, twice as massive as today. A normal planet with a normal core-to-mantle ratio, like Earth or Mars. Then something massive approached. A protoplanet 1.5 to 4.5 times proto-Mercury's mass, possibly proto-Venus or proto-Earth. It hit at a shallow angle, 30 to 45 degrees, traveling at 10 to 20 kilometers per second. Not a direct smash, a cosmic sideswipe. The collision ripped away 60% of proto-Mercury's rocky mantle, but didn't vaporize it completely. The mantle material, torn off in chunks, began falling back toward both bodies. But the early sun was different. Its magnetic field was 10 to 100 times stronger. Its solar wind, a stream of charged particles, was ferocious. That wind hit the floating debris like a cosmic broom, sweeping it away before it could fall back onto Mercury. Within a million years, the stripped mantle material was gone, pushed into interstellar space, or absorbed by other growing planets. What remained? A planet dominated by its iron core. Mercury, as we know it. An accident that shouldn't exist. Mercury's story isn't just about our solar system. Astronomers have discovered thousands of exoplanets. Some are hot Jupiters, gas giants orbiting close to their stars. Some are super-Earths, rocky worlds larger than Earth. But iron-rich worlds like Mercury? Surprisingly rare. Computer simulations show that forming a Mercury requires specific conditions. The right impact angle, the right impactor size, the right timing, and a young star with a strong enough wind to clear the debris. Change any variable, and you get a different outcome. Mercury is a cosmic lottery winner, or maybe a cosmic lottery loser, depending on how you look at it. It survived, but it survived by losing everything except its heart. Jupiter tilts 3 degrees. Saturn tilts 27 degrees. Earth tilts 23.5 degrees. The tilt that gives us seasons. Neptune tilts 28 degrees. And Uranus? 98 degrees. Uranus doesn't spin upright. It doesn't even spin at a dramatic angle. It rolls. It orbits the Sun on its side, its north and south poles facing east and west. One pole gets 42 years of continuous sunlight, then 42 years of total darkness. Every planet in the solar system should have formed spinning in roughly the same direction, from the same rotating disk of gas and dust. So what knocked Uranus sideways? The obvious answer: a giant impact. For decades, scientists assumed that an Earth-sized object slammed into Uranus billions of years ago, knocking it over. 2018 computer simulations by Jacob Kegeris at Durham University showed that a collision with an object roughly twice Earth's mass could tilt Uranus by 98 degrees. But there was a problem. Uranus has 5 large moons: Titania, Oberon, Umbriel, Ariel, Miranda. They all orbit around Uranus's equator, not the solar system's orbital plane. If Uranus was suddenly knocked sideways, its moons should have kept orbiting in their original plane, crossing from pole to pole. But they didn't. Worse, simulations showed that a single massive impact would create moons orbiting backwards, retrograde motion. Uranus's moons orbit prograde, in the same direction as the planet's rotation. One giant impact doesn't work. In 2011, Alessandro Morbidelli and his team at the Observatory of Côte d'Azur proposed something different. What if Uranus was hit twice? Not one massive collision. 2 Earth mass impacts early in Uranus's history, before its moons had formed from the surrounding disk of gas and dust. The first impact tilts Uranus part-way. The debris disk around the planet reforms, aligning with the new tilted equator. The second impact finishes the job, knocking Uranus to 98 degrees. The disk, now twice enriched with impact debris, flattens into an equatorial disk. And from that disk, the moons form, already aligned with Uranus's new tilted equator, orbiting in the correct prograde direction. The research revealed something profound. The fact that Uranus was hit at least twice suggests that significant impacts were typical in the formation of giant planets. The standard theory of planet formation, that planets gently grew by accumulating small objects, was wrong. Violence was the rule, not the exception. A 2022 study offered another possibility. What if a massive moon, not an external impactor, tilted Uranus? A moon forming early in Uranus's history could have gravitationally destabilized the planet, pulling it sideways over time before crashing into Uranus and vanishing. We may never know for certain which theory is correct, but either way, the answer is violence. Today, the solar system is quiet, stable, predictable. We can calculate where planets will be centuries from now. Asteroids mostly stay in the asteroid belt. Comets swing by on schedule. But it wasn't always this way. Between 4.5 and 3.8 billion years ago, space between the planets was full of debris. Planetesimals, failed planets, mountain-sized asteroids, icy bodies, left over from the solar system's formation. The planets acted like cosmic vacuum cleaners. Every time they encountered debris, their gravity either pulled it in, adding to their mass, flung it into the sun, ejected it from the solar system entirely. Eventually, the planets cleared their neighborhoods, the defining characteristic of a planet. Pluto never did, which is why it was demoted. By 3.8 billion years ago, most of the large impactors were gone. The planets settled into gravitational resonances, mathematical relationships between their orbits that create stability. Jupiter and Saturn avoid crossing a dangerous 2-to-1 resonance. Neptune and Pluto are locked in a 3-to-2 resonance, ensuring they never collide, despite Pluto crossing Neptune's orbit. What remained became the asteroid belt, thousands of objects too far apart to collide and merge, shepherded by Jupiter's gravity. And the Kuiper belt and Oort cloud, frozen reservoirs of comets at the edge of the solar system, leftovers from formation. The violence didn't stop completely. Asteroids still hit Earth. The dinosaurs learned that 66 million years ago. But the era of planet-shaping collisions, over. The battlefield had cooled. The survivors remained. Mercury with its naked core, Earth with its stolen moon, Mars with its split face, Uranus rolling sideways. Every scar tells a story, and every story begins with violence. Our solar system isn't special. Computer simulations show that giant impacts are common in the final stages of planet formation, almost inevitable. Somewhere in the galaxy right now, a Theia is colliding with a proto-Earth. A proto-Mercury is being stripped of its mantle. A proto-Uranus is being knocked sideways. And when we discover exoplanets with strange compositions, unusual tilts or peculiar moons, we'll know why. They're not broken. They're not mistakes. They're survivors. Look at them again, the planets. Mercury, stripped to its core, but still orbiting after 4.5 billion years. Earth, wearing a moon torn from its own body, the collision that made life possible. Mars, split in two, carrying the evidence of violence written on its face. Uranus, knocked sideways, rolling through space in defiance of every rule. These aren't flaws, they're stories. Every scar tells you how a world survived. The early solar system was a forge. Everything that couldn't survive the violence was destroyed. What remained? The strong, the lucky, the resilient. And they're still here, still orbiting, still bearing witness to the war that built everything. But here's what doesn't make sense. Mars's biggest volcano is twice the height of Mount Everest, but Mars has been dead for billions of years. Io, a moon smaller than our moon, erupts like hell itself. And Enceladus, a frozen moon, shoots geysers of water into space. The collisions are over. The planets should be cold, dead. So why are some worlds still burning? This is Cosmic Canvas, where we reveal the hidden stories written in worlds. Until next time, look up. Every world has a story, and every story begins with survival.